The study examines the cultural value differences exhibited by large language models, LLMs, when prompted in different languages and with varying model sizes. It focuses on three variants: question ordering, prompting language, and model size. The experiments reveal that each tested LLM can efficiently exhibit different cultural values, with relatively consistent cultural values when presented with prompts in a single language. Interestingly, the prompting language can influence the expression of cultural values, with the same question eliciting divergent cultural values when queried in a different language. Differences in model sizes have a more significant impact on their demonstrated cultural values than model differences. The results suggest that query language and model size are the main factors resulting in cultural value differences. The authors of this study delve into the cultural values exhibited by large language models, LLMs, through a comprehensive experimental pipeline. They utilize Hofstede's Value Survey Module, VSM, a data collection instrument that quantifies cultural values across 6 dimensions, to contextualize LLM responses to the VSM questionnaire. Their findings indicate that LLMs consistently demonstrate similar cultural values within a single language, despite variations in prompt content, but are affected by alterations in option positioning. Notably, LLMs show different cultural values across different languages, and differences in the cultural values expressed by models correlate with variations in text generation proficiency. The authors also review related work in detecting social and cultural biases displayed by models. Previous studies have assessed social and cultural biases in language models, incorporating social science models for direct evaluation of the values inherent in the models. These approaches include fine-grained local biases and high-level global biases, as well as innovative methodologies employed to evaluate bias and values in large language models. The challenges in mitigating biases in generated text are acknowledged, as biases can be inherited from human language and culture in training data. The authors discuss social science models, such as the political compass test and Hofstede's Value Survey Module, which have been integrated into understanding language models' values. These models have been used to map the political leaning of language models and explore cross-cultural values embedded in multilingual masked language models. Language models have been found to express cultural values, although previous studies have struggled to establish strong correlations with value surveys. Recent research has highlighted the context-dependent nature of language model behavior, where even minor perturbations can significantly impact their performance. The current practice of prompting has been deemed insufficient to accurately capture model perceptions. This study aims to systematically evaluate the expression of cultural values by models under varying circumstances, including the effects of prompt engineering, language differences, and model capabilities. The Value Survey Module, VSM, is utilized to measure cultural values, as outlined in Hofstede's cultural dimensions theory. The VSM is a 24-question questionnaire that evaluates cultural values across 6 dimensions: power distance, individualism, uncertainty avoidance, masculinity, long-term orientation, and indulgence. Each dimension is calculated using a formula with the raw scores from 4 survey questions. Experiments are conducted using prompts derived from the VSM questionnaire, delivered in a zero-shot manner. The language model is expected to respond in JSON format, specifying the chosen option ID and the rationale behind the selection. Prompts are designed to provide context for the model's responses, including simulated background identities, nationality, age, and gender. The experiment consists of multiple sets, each defined by a unique combination of 3 hyperparameters: the tested language model, the prompt language, and whether options are shuffled. Within each set, the language model is presented with a curated collection of simulated identities, and each question is queried 10 times with different seeds, resulting in a total of 12,960 responses for each experiment set. This systematic evaluation aims to provide insights into the expression of cultural values by language models under varying conditions, ultimately contributing to a deeper understanding of their behavior and decision-making processes. To analyze the simulated identities, the average of the 10 outputs for each identity is calculated, serving as a single data point in the experiment set. Pearson correlation coefficients and p-values are computed among centroid vectors to evaluate relationships between groups. Furthermore, vector space model (VSM) scores are generated for each nation from the 24D vectors, and the standard deviation is used to assess dimensional disparity. The model cultural disparity (MCD) is defined as the ratio of the overall disparity among nations observed in each experiment set to the distance among nations observed for humans, providing a quantifiable measure of cultural disparity. Clustering methodologies, including the Davies-Bolden index and the silhouette score, are employed to assess the effectiveness of separation between experiment sets. Notably, a novel measurement method, the silhouette score with human reference, SSH, is introduced to measure the absolute disparity between pairs of sets, using human results as the reference point. This approach enables the evaluation of the absolute difference in cultural disparity between experiment sets, relative to human cultural norms. Large language models have been increasingly used to express cultural values, but their consistency and sensitivity to contextual changes remain unclear. To address this, a study was conducted to investigate the expression of cultural values by large language models. The experiment employed several models, including members of the Llama 2 and Quen families, as well as Mixtral, to explore three key research questions. Firstly, can large language models consistently express cultural values in a single language? Secondly, how does language affect the expression of cultural values in models? And finally, what can be inferred about models' expression of cultural values when comparing them? To answer these questions, the experiment involved a comprehensive setup. Prompt variants were designed to simulate identity and manipulate options order, allowing for an evaluation of the model's consistency and sensitivity to contextual changes. This enabled the researchers to assess the model's ability to express cultural values in a nuanced and context-dependent manner. By exploring these research questions and using a rigorous experimental design, this study aims to provide insights into the capabilities and limitations of large language models in expressing cultural values. The findings have significant implications for the development of more culturally sensitive and context-aware language models. The paper examines the consistency of cultural values in AI models despite selection bias. It analyzes changes in the distribution of raw scores and measures the interset disparity between experiment sets for each model. The results show that most models maintain highly correlated score distributions after option shuffling. However, the overall correlation scores are lower than those calculated for simulated identities. This suggests that models remain vulnerable to selection bias and fail to maintain consistent cultural values in the face of textual ambiguities. The experiment also indicates that language impacts the model's choice of options more significantly than the shuffling of option order. The analysis begins by visualizing the 6 DVSM scores for different experiment sets using TSNE, highlighting discrepancies between initial measurements and SS. It emphasizes the importance of considering interset distance with human disparity, demonstrating how language significantly influences model responses and cultural values expressed. The comparison of models reveals patterns of cultural values, with heat map charts representing comparisons among models queried in English, Chinese, and cross-language settings. Notably, models from the same family do not necessarily exhibit closer cultural value alignment, and larger models within the same family show better text generation performance due to their ability to handle complex patterns and generalize better to unseen data. In the realm of natural language processing, a significant challenge emerges when evaluating cultural values expressed by language models across different languages. The MMLU test and SSH values have been employed to assess these disparities, revealing a correlation between the two metrics. However, it is crucial to note that a small gap in MMLU scores does not necessarily translate to a small SSH value, suggesting that language variations can cause substantial differences in cultural values among models. This research underscores the importance of understanding how language model performance influences the expression of cultural values. To address this issue, future studies aim to develop a comprehensive testing mechanism that evaluates not only text quality but also the expression of cultural values and their alignment. This will provide a more nuanced understanding of how language models reflect and perpetuate cultural norms and values. The findings from this study contribute to the ongoing discourse on the role of language models in shaping cultural narratives. By examining the disparities in cultural values expressed by these models, researchers can better comprehend the impact of linguistic and cultural factors on AI development. This knowledge is essential for creating more inclusive and culturally sensitive language models that can effectively communicate with users from diverse backgrounds. Ultimately, this research serves as a stepping stone towards a more equitable and culturally aware AI, highlighting the need for continued exploration into the complex interplay between language, culture, and technology. This section of the research paper addresses the limitations of the study and outlines potential avenues for future research. The authors acknowledge that their exploration of cultural values expressed by models was limited to the 24 questions of the VSM 2013 survey, which has been criticized for its simplicity. They propose that future studies should incorporate additional cultural value surveys to further investigate the model's behavior. Another limitation is the evaluation of only 6 models, which the authors suggest should be extended to include additional models to validate the findings regarding the model's expression of cultural values and their performance differences. The authors also note that their experiments were conducted in a narrowly defined context, prompting models to generate responses in a zero-shot manner, conditioned solely on the provided context. They suggest that future studies should explore how models express cultural values when supplied with extensive past experiences and acting as believable agents. Furthermore, the authors highlight the need for a new evaluation pipeline or mechanism to assess and quantify the relationship between specific cultural value patterns and the generated text's quality. This would build upon the current finding that variations in text quality result in different cultural values. Additionally, the authors recognize that language-induced disparities in cultural values may impact users and propose that future research should develop a systematic approach to assess these disparities and formulate strategies to mitigate any negative effects. In the section on ethical considerations, the authors emphasize that their analysis relies on data from the widely recognized Value Survey Module, VSM, 2013 and utilizes open-source language models. They clarify that although their research examines the responses of various large language models to assess cultural values, they explicitly avoid ranking these models to maintain objectivity and ethical integrity. The literature review on bias in large language models emphasizes the significance of understanding and mitigating bias, particularly in terms of cultural and social aspects. It begins by referencing Ferreira's work, questioning whether chatbots should be biased, and then cites Garrido-Muñoz et al.'s survey on bias in deep NLP, highlighting the need for a nuanced understanding of cultural dimensions. The concept of cultural dimensions is explored, referencing Hofstede's VSM 2013 scales, which measure cultural differences across countries. The authors also mention Gerlach and Aixin's study on the external validity and internal consistency of Hofstede's scales. The discussion turns to the importance of modeling social factors of language, citing Hovey and Yang's work on social factor modeling. Additionally, the CBBQ dataset is referenced, curated with human-AI collaboration for large language models. The review explores various aspects of bias, including gender bias, nationality bias, and cultural perspectives, as well as studies on understanding and mitigating social biases. It concludes by referencing several other studies on language models, emphasizing the importance of considering cultural and social factors in their development and evaluation. The authors present a comprehensive list of 15 constraints that govern the optimization problem in robotic grasping and manipulation. These constraints are categorized into 3 groups: kinematic, dynamic, and task-oriented. Kinematic constraints encompass the robot's joint limits, end effector pose, and grasping constraints. Dynamic constraints include the robot's dynamics, contact forces, and frictional forces. Task-oriented constraints involve the object's pose, shape, and weight, as well as the task requirements. The authors use a nonlinear optimization framework to solve the constrained optimization problem. This framework is formulated as a nonlinear programming problem, where the objective function is a weighted sum of the task-oriented constraints. The optimization problem is solved using a sequential quadratic programming algorithm, which iteratively updates the solution until convergence. The authors also present a detailed analysis of the constraint Jacobian matrix, which is a crucial component in the optimization framework. The constraint Jacobian matrix is used to compute the constraint gradients, which are essential for the optimization algorithm. The authors derive the analytical expression for the constraint Jacobian matrix and discuss its properties. Furthermore, the authors discuss the importance of constraint prioritization in robotic grasping and manipulation. They propose a constraint prioritization scheme based on the task requirements, which ensures that the most critical constraints are satisfied first. This scheme is integrated into the optimization framework, allowing the robot to adapt to changing task requirements. Overall, the authors provide a comprehensive framework for robotic grasping and manipulation, which takes into account the various constraints and task requirements. The proposed framework has the potential to enable robots to perform complex tasks in real-world scenarios. The investigation pipeline, as depicted in Figure 3, consists of 3 steps. The first step evaluates cultural values exhibited by a language model, LLM, queried with variants of prompts in a single language. The second step assesses cultural values in the context of different languages. The third step examines cultural values exhibited by different LLMs, including those within and across model families and in various model sizes. This pipeline is supported by prompt samples, such as those in Figure 4, which include customized components embedded with respective values for querying the model. The research paper presents a comprehensive analysis of cultural values in language models, utilizing the VSM framework to quantify these values. Cultural values are introduced as a crucial aspect in understanding and interpreting the behavior of language models, which are increasingly used in various applications. To measure cultural values, the authors employ the VSM dimension formula, consisting of 6 dimensions: power distance index, PDI, individualism versus collectivism, IDV, masculinity versus femininity, MAS, uncertainty avoidance index, UAI, long-term orientation, LTO, and indulgence versus restraint, IVR. Each dimension is calculated using specific formulas, as shown in equations 6 through 11. The authors conducted experiments with simulated identities representing 9 different nationalities: USA, China, France, Germany, Brazil, India, Singapore, Japan, and South Africa. The results of these experiments are presented in Table 3, showing the mean VSM scores for each nationality. These scores provide insights into how cultural values are perceived and represented in language models across different nationalities. In addition to the experiment results, the authors also provide the mean values for each VSM dimension for all experiment sets and human results, as outlined in Table 4. This information is crucial for understanding the overall cultural values embedded in language models and their implications on various applications. The paper also discusses clustering measurement methods, specifically the Davies-Bolden index, DBI, which quantifies the average similarity between each cluster. The DBI value is calculated using equation 12 and provides an overview of the disparity in models' cultural values at the experiment set level. A lower DBI value indicates better separation between clusters, while a value larger than 1 suggests that the separation between clusters is not very distinct. Overall, this section of the research paper focuses on the quantification of cultural values in language models using the VSM framework and clustering measurement methods. The findings presented here contribute to a deeper understanding of how cultural values are represented and perceived in these models, which is essential for developing more culturally sensitive AI systems. The value stereotype model, VSM, dimensions, including power distance index, PDI, individualism versus collectivism, IDV, masculinity versus femininity, MAS, uncertainty avoidance index, UAI, long-term orientation versus short-term normative orientation, LTO, and indulgence versus restraint, IVR, are presented with their mean values for various experiment sets and human results in Table 4. To maintain consistency with human results in Table 3, these mean values are presented in integer format. The silhouette score, SS, metric is introduced to evaluate the clustering quality of model outputs. This metric compares each point's similarity to its cluster against other clusters. The formula for the silhouette score S, I, of a single model output I is given by equations 13-15, where a pi represents the mean distance of data point pi to all other data points in the same set C1, and b pi represents the mean distance of pi to all points in the opposite set C2. The SS metric ranges from 1 to 1, with higher values indicating more effective separation between clusters. The subsequent section presents the experiment results for research question 1, RQ1, focusing on variant context results based on the raw scores of 24 questions, as listed in Table 5. An experiment was conducted to assess the cultural values expressed by AI models in response to prompts featuring different simulated identities. The experiment involved querying models with single-language prompts and analyzing their responses using the Pearson correlation coefficient, PCC, which measures the linear correlation between two variables. The results, presented in Table 5, show strong correlations between model responses for each identity context, with average correlation coefficients computed over grouped identity contexts and significantly low p-values. However, correlation coefficients below 0.9 indicate weaker correlations in certain cases. In addition to PCC, the study employed two other metrics: mean character distance, MCD, and vector space model, VSM, scores. Table 6 reveals a high degree of similarity between responses generated by different models within each set, with the largest MCD being less than 0.7. Table 7 presents the raw scores of 24 questions for each pair of experiment sets, while Table 1 provides the results for interset comparison based on VSM scores for each pair of experiment sets. The Davies-Bolden index, DBI, values, which measure the similarity between clusters, exceed 0.5 for all models, indicating poor clustering quality. Similarly, the silhouette scores, SS, which evaluate how similar an object is to its own cluster compared to other clusters, are below 0.7, further supporting the notion of ineffective clustering. Most models have SSH values less than 1, except for Qwen14b chat, which has an SSH value exceeding 1. Suggesting a greater disparity than human results. The study also explores the impact of language differences on cultural values expressed by the models. Tables 8 and 2 present the results, which demonstrate that language does not significantly influence the cultural values expressed by the models, with average DBI values of 0.17 for comparisons based on language differences. Overall, the results demonstrate that the cultural values expressed by the models are highly correlated and exhibit poor clustering quality, regardless of language or shuffling of options. These findings highlight the need for further research into the cultural values expressed by AI models and how they can be improved to better reflect diverse perspectives. Dimensional standard deviation and distance metrics are employed to assess various models and human results, revealing the significant impact of simulated nations on the expression of cultural values in models. A comparative analysis is conducted to examine the effects of language differences on model responses. Specifically, the study investigates whether asking the same questions in different languages versus shuffling responses yields distinct outcomes. The findings indicate that language differences lead to increased variability in model responses, with an average increase of 42.7% in the sum of squares, SS, value for language comparisons. This phenomenon is visually supported by the T-distributed stochastic neighbor embedding, TSNE, figures in Figure 1, which illustrate the proximity of certain models, and the heat map in Figure 2, which highlights the variability in responses. These results suggest that linguistic factors significantly influence the model's expression of cultural values, underscoring the importance of considering language differences in cross-cultural comparisons. The study's insights have implications for the development of more culturally sensitive AI models, capable of capturing the nuances of human cultural expression. The consistency of responses from various models across different prompts and languages is a key area of discussion. Pearson correlation coefficients and p-values are presented for models' responses between W shuffle and with O shuffle options, as well as between English and Chinese prompts. These results indicate that models from the Llama 2 and Qwen families exhibit the smallest differences within their own family when queried in Chinese. A heat map in Figure 2 visualizes the SSH values between models when questioned in different languages, revealing significantly larger differences in cultural values when comparing models across languages. This suggests that the dimensional space used in the VSM testing might be too constrained, leading to overlap in results from various experiment sets. The Visual Satisfaction Metric (VSM) questionnaire is a crucial tool for evaluating the perceived visual quality of generated images. Comprising 10 questions, the VSM questionnaire assesses the visual appeal, naturalness, and overall quality of images, capturing human perception of image quality. To mitigate subjectivity, the questionnaire employs a pairwise comparison approach, where participants select the better image for a specific attribute, such as more realistic or more visually appealing. The questionnaire is divided into two sections. The first, questions 1-5, focuses on visual appeal, including naturalness, realism, and overall quality, while the second, questions 6-10, evaluates the image's ability to convey information and evoke emotions. The VSM score is calculated by aggregating responses to each question, with higher scores indicating better visual satisfaction. This novel approach provides a standardized and quantifiable method for evaluating visual quality, leveraging human perception to identify subtle differences in image quality that may not be captured by traditional metrics, such as peak signal-to-noise ratio, PSNR, or structural similarity index, SSIM. The VSM questionnaire has significant implications for the development of image generation models, providing a more accurate and reliable means of evaluating their performance. Its applicability extends to a wide range of computer vision tasks, including image synthesis, image-to-image translation, and image editing. The Visual Semantic Mapping (VSM) questionnaire is a pivotal tool for evaluating the effectiveness of the proposed methodology in capturing and representing complex spatial relationships between objects within an environment. This questionnaire consists of multiple-choice questions and open-ended queries designed to elicit both quantitative and qualitative feedback from participants. The first section of the page includes multiple-choice questions that focus on the clarity and accuracy of the visual representations generated by the VSM algorithm. These questions aim to understand how well the algorithm can capture and convey spatial information, object properties, and their relationships in a scene. For instance, one question asks, how accurately do you think the visual representation reflects the actual spatial relationships between objects? With options ranging from very accurate to not accurate at all. The second section comprises open-ended questions that encourage participants to provide detailed insights into their experience with the VSM system. This section allows for a more nuanced understanding of user perception and potential areas for improvement. An example question is, can you describe any difficulties you encountered when interpreting the visual representation? This type of question helps researchers identify any ambiguities or limitations in the current implementation of the VSM algorithm. In addition to these sections, the page also contains a section for demographic information such as age, gender, and level of education. This data can be used to analyze the effectiveness of the VSM across different user groups and to identify any potential biases in the system. Overall, the VSM questionnaire serves as a vital component in evaluating the efficacy of the proposed methodology. By collecting both quantitative and qualitative feedback from participants, researchers can refine the algorithm to better meet the needs of users and enhance its performance in capturing and representing spatial relationships between objects. The Visual Similarity Matrix (VSM) questionnaire, presented in Figure 7, is a crucial component of the proposed methodology. It's designed to facilitate human evaluation of generated images, with each page showcasing a distinct set of images. Page 3 features a 5x5 matrix where participants rate the similarity between each pair of images on a scale of 1 to 5. The VSM assesses the diversity and quality of generated images, enabling the collection of subjective human feedback. This feedback is used to fine-tune the generative model, ensuring high quality and diverse images. The VSM is a novel contribution, providing a systematic approach to evaluating generative models. It enables nuanced and detailed feedback, allowing for a comprehensive understanding of strengths and weaknesses. By leveraging human evaluation, researchers can identify areas for improvement and refine the model. The VSM serves as a critical component in the overall evaluation framework, with results used to validate the proposed methodology's effectiveness and demonstrate its superiority over existing approaches. A key limitation is the reliance on human evaluators, which may introduce subjective biases. Future work involves exploring automated evaluation metrics to increase efficiency and scalability.